I've often wondered if AI models, especially when they're dealing with these massive images and really complex questions, could be a bit smarter about when to actually pay attention to the details. It feels like they should have some, I don't know, human-like intuition sometimes.
That's a really interesting point.
Well, today we're diving into a paper that seems to tackle exactly that thought. We're exploring VisionThink, smart and efficient vision language model via reinforcement learning.
Ah, yes, VisionThink. It's a fascinating piece of work.
It really introduces a groundbreaking approach to how vision language models, VLMs, process visual information. So let's break down the core problem they're tackling and what VisionThink does so brilliantly.
Okay.
VLMs are incredibly powerful, right? But their visual token consumption has just exploded. Think about a modern smartphone photo. It might need hundreds, maybe even thousands of visual tokens for a VLM to process.
Yeah, the numbers are quite staggering.
This exponential growth, it just makes efficiency absolutely critical. Now, the current efficient VLM methods, they often use these fixed compression ratios. But the authors spotted something really crucial.
Which is?
Well, they observed that most real-world scenarios don't actually need super high-resolution images. Performance barely drops. But then, for very specific tasks, like, say, optical character recognition OCR, you absolutely do need that detail.
Right, that makes sense. You need to read the fine print sometimes.
Exactly. So VisionThink, it ingeniously solves this by dynamically deciding when to process a high-resolution image. It actually starts with a downsampled, low-resolution image.
Okay.
And only requests the higher resolution one if that initial fuzzier information isn't enough to solve the problem.
So it asks for more detail only when necessary. That's clever.
It is. And the key outcomes here are pretty significant.
Yeah.
You get major visual token savings for the simpler tasks, but you still keep that strong, fine-grained understanding for complex stuff like OCR.
And they pull this off using reinforcement learning.
Yes, a clever RL approach, and they boost it with this LLM-as-Judge strategy.
Yeah.
So for anyone listening who works with large AI models, researchers, ML engineers, maybe you're just trying to keep up this points towards, more efficient inference, lower compute costs.
And models that are genuinely smarter about how they use resources.
Exactly. Models that are smarter about resource allocation. It's a bold claim, right? But to really get why this is a big deal, we need to dig into the problem VisionThink is actually solving.
It's definitely a critical problem, and you outlined it perfectly. The leap we've seen in general visual question answering, or VQA, with models like Elavi 1.5 and Quinn 2.5 VL, it's been truly mind-blowing.
Absolutely.
But like you said, this progress comes at a substantial cost. That visual token count just keeps climbing.
And it immediately throws up this paradox, doesn't it? The paper highlights it perfectly. They found that for lots of common VQA tasks, think benchmarks like MAME, real-world QA, you can slash the image resolution, say, down to 14 size.
Which is a 75% token reduction.
Right. A huge reduction. And the performance barely dips. You still get accurate answers most of the time.
Exactly. But then you hit those critical tasks like chart QA, OCR bench, things that demand really detailed understanding.
And there, low resolution is a killer.
Absolutely. Performance drops significantly. And this just shows that the level of redundancy in visual info, it varies massively. Depends on the task, it depends on the image.
So that one-size-fits-all compression ratio it doesn't work. It's either inefficient or it hurts performance.
Precisely. Which means those previous efficient VLM methods, the ones that prune or merge a fixed number of tokens based on some threshold, they really hit a wall here.
They just can't adapt.
Right. And beyond that, many of them rely on calculating attention scores to figure out what to prune.
Okay.
And for folks familiar with LLMs, that immediately flags issues. It makes it hard to optimize with modern speed-up techniques like flash attention 2, and it can actually increase memory usage too.
Ah, right. Kind of defeats the purpose of being efficient.
Exactly. Plus, they often aren't compatible with efficient inference frameworks like VLLM, which you really need for practical deployment. So VisionThink is trying to get around all these fundamental limits.
Okay, so if fixed compression is basically a dead end, how does VisionThink actually, flip the script?
Yeah.
This smart pipeline sounds revolutionary.
It really is a paradigm shift. Instead of feeding in the full high-res image and then trying to figure out what's redundant and throw it away, it starts by inputting already compressed visual tokens, so low resolution from the get-go.
Okay, start small.
Then the model itself intelligently decides if that low-res view is enough. If it thinks, I can't answer accurately with this, it can output a special token.
Like a command.
Kind of, yeah. a special token to explicitly request the original high-resolution image. This dynamic processing is the absolute key to its efficiency and its effectiveness.
And to make this actually work, they had to crack two big challenges, right?
Right.
First, how do you even get RL, reinforcement learning, to work effectively for something as diverse and open-ended as general VQA?
That's a huge hurdle. And that's exactly where their LLM-as-Judge strategy comes in. It's really quite clever.
How does that work?
So instead of trying to get the VLM itself to judge its own visual understanding, which can be tricky, they use an external large language model.
Just a standard LLM.
Yeah, an off-the-shelf one. Its only job is to act as a judge. It looks at the VLM's text answer and compares it to the ground truth text answer, purely text-based comparison.
So it avoids any potential bias from the image itself or the VLM's own limits.
Precisely. It keeps the judgment clean, and the reward is super simple, discrete, just 0 or 1, wrong or right, minimizes misjudgment.
Okay, that sounds robust.
And a big plus is flexibility. They could directly use, I think it was 130,000 samples from existing supervised fine-tuning data sets to train the RL agent. No need for a cold start phase.
Right, I remember reading that, because sometimes that cold start pre-training can actually hurt general abilities if the data isn't diverse enough.
Exactly. They found direct RL training, starting from the base Qwen 2.5 VL model, worked better for general VQA.
Okay, so straight into RL. And since VisionThink's whole interaction is multi-turn, try low res, maybe request high res, they needed a smart way to train those sequential decisions.
Right, it's not just one decision.
They adapted this advanced RL algorithm, GRPO, Group Relative Policy Optimization.
That's the one. GRPO is really useful here. It estimates baselines using group scores. Think of it like it groups similar situations together to learn more stably and efficiently.
Reduces computation and makes training more stable.
Exactly. Which is great for these complex multi-step tasks. And for the multi-turn aspect, the key technical trick is masking irrelevant tokens during optimization. You only focus on the actual output generated by the VLM.
Gotcha. So how does the model actually signal, hey, I need the high-res image now? Is it like a specific word it learns?
Pretty much. It learns to output specific special tokens right inside its prompt. That output acts as the trigger for the system to provide the high-resolution image.
And they found a specific prompt format worked best.
Yeah, the Qwen 2.5 VL agent prompt seemed most effective. It lets the model show really distinct different behaviors, like either answer directly or clearly signal for the resize, which makes that GRPO optimization work properly.
Okay, so the model knows how to ask, but then there's the reward function. That seems absolutely critical to stop it from just always asking for the high-res image to play it safe.
You've absolutely hit the nail on the head. That is the core challenge. Get the balance right.
So how did they design the reward?
The total reward, overall, it's basically accuracy plus R format minus this crucial penalty term, pi control.
Okay, accuracy first. That's just the 0 or 1 from the LLM-Judge.
Correct. Simple yes/no on correctness.
Yeah.
Then the format reward, R format.
That's for following instructions, using the right tags, like think and answer.
Exactly. You get a small reward, 0.5 points, for using those tags correctly, and also for getting the JSON format right if it makes a function call, like the resize image call. Just encourages it to follow the instructions properly.
Makes sense. But the penalty, eye control, that sounds like where the magic happens.
It really is, because, like you said, without it, the model just learns, always ask for high res. It gives the best chance of being right.
But the paper mentioned a simple fixed penalty. Didn't work either. It caused this weird collapse.
Yeah, the lucky guesses problem. If you penalize high-res requests too much with a fixed penalty, the model might just give a low-res answer even if it's unsure, if it happens to guess right based on the blurry image.
It gets rewarded for bad behavior.
Precisely. It reinforces making potentially uninformed guesses, so they needed something smarter.
And that's the dynamic penalty.
Yes, an ingenious threshold-based dynamic penalty. Here's the logic. If the model's internal probability of getting the answer right with the low-resolution image is currently low.
It's basically saying, I'm not confident with this blurry view.
Right. In that case, giving a direct answer gets a penalty. This encourages it to make the high-resolution request instead.
Okay. And the flip side.
Conversely, if the probability of answering correctly with low res is high, the model feels confident, then requesting the high resolution image gets a penalty.
So it encourages the direct, efficient answer when appropriate.
Exactly. This adaptive penalty prevents those collapses, keeps the image resize call stable and reasonable, and essentially forces the model to develop a kind of self-awareness about its own uncertainty. It learns when it needs more info.
That is really clever. And to train that smart decision-making, they needed the right kind of data. How did they prepare that?
They put together a specific data set, roughly 10,000 samples that genuinely required high-resolution processing, and another 10,000 that were fine with low-res.
And how do they know which was which?
They used their base model, ran it multiple times, multi-rollout, at different resolutions, and classified the samples based on whether accuracy improved significantly with high-res.
Okay, so they built a data set tailored to teach this specific decision. Now, on to the results. Did it actually work?
The experimental results really back it up. They tested VisionThink across a whole range of VQA benchmarks. Well, broad ones like MME, Real World QA, MMVet, POKEP, MathVerse, your general visual Q&A, but also those really specific, detail-heavy ones like ChartQA, OCR Bench, and MathVista, the ones testing if it can read tiny text or understand charts accurately.
Right, and I noticed they mentioned adjusting the ChartQA evaluation, calling it ChartQA. Why was that?
Yeah, that's an important technical point. The original ChartQA evaluation script had some known quirks, especially with how it compared numbers or percentages. Sometimes it would mark a basically correct answer as wrong because of tiny floating point differences.
So it wasn't always reliable for fine-grained tasks.
Kind of. So their ChartQA adjustment used a GPT-4o-based judge plus human checks just to get a more accurate, reliable score on that really detail-dependent benchmark.
Okay, good to know. So with that careful evaluation, how did VisionThink actually stack up?
It performed very well. VisionThink, the full version, and also VisionThink, the one trained just with the LLM-as-Judge. They both showed comparable or even better performance than the original base model, Qwen 2.5 VL7B.
Any standout improvements?
Yeah, quite notable gains on MathVerse, up by 3.7%, and MMVet, a really impressive 8.9% gain over the base. And interestingly, VisionThink actually beat all the closed source models they compared against on the MME benchmark, hitting a score of 2,400.
Wow. So that LLM-as-Judge strategy really does seem to boost the core reasoning ability.
It certainly looks that way. It's not just about efficiency. It seems to make the model genuinely better at answering questions, too.
Okay, accuracy is great, but what about the efficiency side? Inference time is a huge factor in the real world.
Definitely. And here, VisionThink shines too. Its inference time is significantly better than models that just chew on the full resolution image all the time, like the baseline QuenRL.
How much better?
It's actually pretty close in speed to models that only ever see the 14 resolution images, like QuenRL 14, at least on most benchmarks. For example, they reported it being more than twice as fast on Doc VQA and about a third faster on MME and POKEP.
That's a significant speed up. But I remember the paper noting something interesting. On those really OCR heavy benchmarks like ChartQA, VisionThink might actually take more time than the baselines. That sounds weird for an efficient model.
It does sound counterintuitive at first, but that's what they call the smart time consumption aspect. It's actually a feature, not a bug.
How so?
On those specific tasks where high detail is crucial, VisionThink correctly identifies the need for the high-resolution image and requests it. This naturally leads to processing more tokens overall for that specific instance.
So it's choosing accuracy over blind speed when necessary.
Exactly. It's making a calculated trade-off. It's saying, okay, for this question about this detailed chart, I absolutely need the high-res view to get it right, and it's worth the extra computational cost.
That makes sense. It's intelligently allocating resources. And this ability seems way better than older efficient VLMs like FastV or sparse VLM.
Yes, the paper shows VisionThink outperforms them on average across 9 benchmarks, especially on those OCR-related tasks where the older methods tend to struggle because they use fixed pruning. VisionThink doesn't need a predefined ratio. It decides for itself, image by image, question by question.
So it's not just about being fast all the time. It's about being smart about when to be fast and when it's worth slowing down slightly to get the right answer.
Precisely.
Which leads perfectly into this idea of the truly smarter VLM, the dynamic resolution calls. It's almost like teaching a kid to read. They skim easy words, but slow down for tricky ones.
That's a fantastic analogy. And VisionThink really demonstrates that kind of intuitive, almost human-like decision process. You see it clearly in the stats.
Like how?
On those OCR benchmarks, ChartQA and OCR Bench, it shows a much higher ratio of requesting the high-resolution image. About 79% of the time for ChartQA, 62% for OCR Bench. It knows detail is critical there.
Okay, so it calls for help when needed. And on the flip side, general VQA.
On the more general benchmarks like MME or DocVQA, the vast majority of samples, we're talking 70% or more, get answered directly using just the low-resolution image. For DocVQA specifically, it only requested high-res about 7% of the time.
Wow, that's a massive token saving on average then.
Huge savings. And it really does align with our own intuition, doesn't it? When you glance at a document, you don't read every single word unless you're searching for something specific or hit a complex part.
You only zoom in when necessary.
Exactly. And the paper has some great qualitative examples showing this, like an OCR heavy document where other methods fail, but VisionThink says, hang on, need to upscale this, and then answers correctly.
Or reading a chart, getting the exact number right after upscaling while others guess.
Yes, or even a simple image query like, are there fire hydrants here? If the low res isn't clear enough, VisionThink smartly upscales to check, finds it, while other models might just say no based on the blurry view.
That feels like AI common sense starting to emerge.
It does. Which brings us to the broader context here. VisionThink isn't really just another token compression trick. It's more fundamental. It feels like a new paradigm for how VLMs process images. That dynamic decision-making really sets it apart from methods stuck with fixed thresholds or pruning strategies.
And crucially, it sounds like it could potentially be combined with other methods.
That's a key point the authors make. It could potentially be integrated with existing efficient VLM techniques, maybe boosting their direct answering accuracy and making the whole system even more efficient.
Now, an interesting question they addressed was, why use reinforcement learning for this rather than just supervised fine-tuning?
Right, because you could theoretically try to teach the model when to ask using supervised examples.
But SFT models tend to over-request.
That's what they found. Even trained on high-quality data showing when high-res is needed, SFT models tend to just ask for high-res way too often, especially when it's not needed. The RL approach seems to make the VLM genuinely smarter and more adaptable in its decision-making. The resize calling ratios were much lower and more appropriate with RL.
And we already touched on why no cold start pre-training, basically, direct RL on the base model maintained better general abilities.
Exactly. Now, it's not perfect, of course. There are limitations.
What are the current ones?
Well, right now it's focused on just 2x resolution upscaling, and the interaction is limited to, at most, 2 turns the initial low-res attempt and potentially 1 high-res request.
So future work could explore more options.
Definitely. Things like more flexible upscaling factors, maybe incorporating other visual tools like cropping specific regions, or even enabling more turns of conversation involving different image tools to tackle even more complex visual reasoning problems.
The authors seem hopeful this will spur more research.
Yeah, they explicitly say they hope VisionThink inspires more work on efficient reasoning VLMs, pushing models towards being smarter and more human-like in how they approach visual information.
So let's wrap this up. What does this all mean for you, the listener, the researcher, the engineer, trying to stay current?
Well, I think VisionThink offers a really exciting glimpse into a future where AI isn't just raw power, but also has discernment. It knows when to spend its valuable computational budget.
And that's not just about saving money or energy, right?
Yeah.
It's about making VLMs truly adaptive, more capable in the messy, diverse real world.
Absolutely. It's about building models that can handle variety intelligently.
Which leaves us with a final thought to mull over.
If AI models can learn to essentially think about how they should look at an image before just jumping to an answer, what other kinds of adaptive, resource-aware intelligence could this unlock?
Especially for really complex, multimodal reasoning tasks.
Exactly. How might this dynamic, self-aware approach shape the design of future AI systems? Perhaps systems that feel a little more human-like in their problem-solving.
Definitely something to think about. A fascinating direction for AI efficiency and intelligence.